about this. We've got to create the model. Our first experiment, we put down here that we wanted to add an extra layer with more hidden units. Yes, but it looks like our model may be too complex for our data set, so that it's not even, it's so large that our data set is not large enough to teach it anything. So what we might try to change is, we haven't looked at anything in number 2. Now, can we alter the learning rate? So the learning rate is 0.01. How about we try Old Faithful Adam? So there's a few different optimizers here. SGD and Adam are probably the most popular. If SGD doesn't work, try Adam. Let's see what happens. Ho ho ho! Look at that! Yes! Oh! That's so far so good. That looks like it's doing better than the previous model. All right, evaluate the larger model. Ho ho! Look at that. Now, we've just, if we go insurance model, where's the first one? Dot evaluate, X test, Y test. What were the metrics from this one? MAE, holy goodness. We've just decreased it by 2,000. So about 30 odd percent, around about. 30 odd percent decrease in error rate by tweaking 2 little things. We added an extra layer and we changed the optimizers. Again, this might not always work, but that's just one of the levers that you can turn on your models to improve them, or at least try to improve them. We put that up here on purpose to try and improve our model. So I'm going to put here, we actually modified this experiment, add an extra layer and use the Adam optimizer. So this one we're going to train for longer, same as above, but train for longer. Maybe 200 epochs. 500 probably too many. Well, who knows? If in doubt, run the code, experiment. Okay, so that's insurance model 2. Let's run insurance model 3, see if we can improve on this number here. How do we create this? So set random seed. So TF random set seed 42, beautiful. Now, number 1 is create the model, same as above. So we'll go insurance model 3 equals TF Keras sequential. Go right to the end here. TF Keras layers. The first layer we had there was a dense layer with 100 hidden units. And now we have TF Keras.layers dense 10. And then TF Keras layers dense 1. Got to make this insurance company happy, you know. What's step number 2? Compile the model. Beautiful. Insurance model 3 dot compile. Loss equals TF Keras losses dot MAE. That deleted itself out of nowhere. The optimizer is, remember what optimizer are we using now? We're using Adam. Optimizers. Come on, Daniel, you can remember that. And then the metric is MAE. Wonderful. And now let's have a look. Number 3 is fit the model. Insurance model 3 dot fit X train Y train epochs equals 200. We might actually put this history equals that. You'll see what this means in a second. So you ready? Let's run this. 3, 2, 1. All right. We're past 100 epochs. Oh yes, the MAE is going down. Beautiful. Woohoo! All right, so if we go, now let's evaluate. Evaluate our third model. Dot evaluate. Do these results on the training data set translate to the test data set? Because that's what we're really concerned about. Evaluate. That is what's up. We've decreased our MAE to 3,500. I believe we are now, so if we look at back to our first insurance model evaluate, X test, Y test, we just halved our error rate in about 5 minutes. How cool is that? Now, there's a few more levers that we could try, but there's also a little thing that I want to show you. And we saved history equals insurance model 3.fit. What is this history variable? Well, this is something we're also going to get very familiar as we go. So plot history, also known as a loss curve or a training curve or a training curve. So how we can do this, if we go pd.dataframe equals history. So history has a history parameter saved to it, or attribute, sorry. And then if we go dot plot, inside a pandas data frame that is, and then we're going to set the y label to loss, and then the x label to epochs. And shift and enter. Look at that. One of the most beautiful sights you will ever see in machine learning and deep learning is a loss curve decreasing. So, why is this so beautiful? It's because if we look at where this history variable originates from, we instantiated it when we started to fit our model to the training data set, specifically insurance model 3. Now, if we scroll right back to the top of the epoch chain here, all the way up to 0 out of 200, look at this. The loss starts at a massive 13,273. So the MAE, when our model first started to learn, its average prediction was off by 13,273, which is basically the average of the whole data set. But then we scroll down, as our model trains, as it learns, its loss goes down, its MAE goes down, and we finish off with a loss of 3,600, and because our loss function is MAE, we finish with an MAE of 3,600 as well. And this is what this curve is reflecting. So when we're training our neural networks, generally we want our loss curve to go down, because that means that the predictions our model is making are becoming less and less wrong. So it actually looks like our model's loss would probably keep decreasing, maybe not as extensively as it has here if we kept it training for longer. So that's probably a little extension that I'll leave for you to try out for yourself. Train the insurance model 3 for a few more epochs, maybe another 100 or 200 or so, and see how low the loss will go. But you're probably asking, after seeing this, how long should you train for? Well, that's a great question. Let's put that there, actually. We'll do the question emoji. Question. How long should you train for? So if you're asking that, I'm going to hit you with an answer that's going to say, it depends. Remember how machine learning and deep learning is very experimental? Well, how long should you train for is, it actually really depends. Really. It depends on the problem you're working on. However, many people have asked this question before. So, TensorFlow has a solution. It's called the early stopping callback. And we're going to use this in a later video, but I just want to introduce it now so it seems familiar. So TensorFlow early stopping callback. Here we go. And essentially what this is this, I'm going to set the link here, early stopping callback. I'll let you read what the documentation says, but I'll just tell you. It's called the early stopping callback, which is a TensorFlow component you can add to your model to stop training once it stops improving a certain metric. So, in the case of our insurance model 3, if we wanted to say train it for 1,000 epochs, we could set the early stopping callback to say, hey, I'm going to set you off train for an unlimited amount of epochs. But once your loss stops decreasing for say 3, 5, or 10 epochs in a row, which means our model has stopped improving, stop training. All right, does that make sense? Now, a little extension you could do would be to look at the early stopping callback in TensorFlow and see how you could implement it for the code that we've written here. All right, but otherwise, I think this video is getting a little bit too long. So we've covered a few modeling experiments here. What we're going to look at next is another way of pre-processing data, specifically normalization and standardization. So again, if you want 2 pieces of extra curriculum before the next video, read up on the early stopping callback and search for what is normalization and standardization, and think about how it might relate to our training data. But anyway, I'll see you in the next video. Welcome back. So in the previous few videos, we've been putting together all of the different concepts that we've learned so far, and there've been a fair few. We started working on a larger example, specifically trying to predict the cost of someone's medical insurance based on features such as their sex, BMI, where they lived, and smoking status. Now, we've got one more thing we're going to cover before we move on to the next section. And it involves pre-processing data, specifically to do with normalization and standardization. Now, you may have heard of these terms before. If not, that's perfectly fine. We're going to go through them. You might be thinking, hey, Daniel, why are we going back to pre-processing data? I thought we already had our data ready. We'd turned it into tensors, we'd one-hot encoded it, etc. And you'd be 100% correct, but there is one step we can do to improve the pre-processing of our data. So if we come back to our keynote here, this is our steps in modeling. And you might have noticed, if you hadn't looked at this in a while, we've actually done each of these steps throughout this entire section. We've gotten our data ready, we've turned it into tensors, we've built a TensorFlow model, we fit the model to the data and we've made predictions on the data, we've evaluated our model through both visualization and using evaluation metrics, we've improved our model through experimentation, and we've saved and reloaded our trained model. But now we're going back to step number 1, possibly the most important step in this entire pipeline, getting our data ready, turning it into tensors. So we've turned all our data into numbers. Remember, neural networks and actually most machine learning models can't handle strings. They need everything to be in numerical form. Number 2, we've made sure all of our tensors are the right shape because, as we've seen before, if our tensors are the wrong shape, we run into a whole bunch of different issues. And number 3, we could do, or we haven't done yet, is to scale features. So normalize or standardize. Now, neural networks tend to prefer normalization. Again, these are just words to you at the moment, but we're going to see what both of these are in a minute. So let's go back to our notebook. Again, if you wanted to figure out what normalization and standardization are, what could you do? Here's what I would do. Let's go, what is normalization in machine learning? If we zoom in here, so we got here, normalization is a technique often applied as part of data preparation for machine learning. The goal of normalization is to change the values of numeric columns in the dataset to a common scale. Without distorting differences in the range of values. All right, so let's have a look at our dataset. X train, or maybe just X as a whole. What does X look like again? So, we see here we've got age, BMI, children, but do you see here how age is on a different scale to what BMI is? So if we go X, what do we want? We want age dot plot. So see how these values are all over the place? That's probably not the best plot. Maybe we can go hist. We want a hist. Oh, we need the kind word. There we go. Okay, so here's the distribution of our age column. Now, what about our BMI column? We want plot kind equals hist. It's like this. So what if we wanted to get these both on a similar scale? So see, this goes from 20 to 60, this goes from 15 to 50, and then children, I'm assuming goes from something, if we go X children dot value counts, what's the max number of children? Value counts. So there's a lot of people with 0 children, and there's a few people with 5 children. So what if we wanted to get these? So 15 to 50, 0 to 5, and 20 to 60. What if we wanted to get all of them, say, between 0 and 1? Well, that's what normalization does. If we come back up here, the goal of normalization is to change the values of numeric columns in the data set to a common scale. Okay, beautiful. Now let's come back to the keynote. Feature scaling. So we have some options here. Now, the scaling type of scale, a lot of different names are used for this, but I'm going to be referring to it as normalization. But if you hear scale features, typically they're referring to normalization. And what it does, converts all values to between 0 and 1 whilst preserving the original distribution. The distribution of our data is just the spread. So here we can see that the most values occur. What's this? This is BMI at about 30. And as we get towards the tails here, the values start to spread out. Whereas the distribution of age is pretty fair along all the values. Maybe most people in our sample are about 20 years old. So we come back here. Now, if we wanted to do this, we can do it with scikit-learn using the min-max scaler. And when should we use it? This is often used as the default scaler with neural networks, and it's the one we're going to get hands-on with. Another very common scaling type is standardization. What it does is it removes the mean and divides each value by the standard deviation. You can use the standard scaler scikit-learn function. And when to use this one? Maybe you want to transform a feature column to have a close to normal distribution. But remember, if we scale our features or standardize our features, this reduces the effects of outliers. So if we come back, this is a normal distribution. Let's have a look. Normal distribution. What does a normal distribution look like? All right, there, also known as a Gaussian. So we come here. If we were to change this age column to be a normal distribution, what would happen? It would reduce the effects of this outlier value here. So see how this column, if we reduce them all to be the shape of that, the tails we might lose out there. Now, what are we going to focus on? We're going to focus on normalization. So if we go here, in terms of scaling values, neural networks tend to prefer normalization. Now, how might we do this? Well, actually, let me just put a little tidbit here. If you're not sure on which to use, you could try both and see which performs better. Now, one more resource I want to show you before we actually get hands-on in code is Jeff Hale's article on scale, standardize, or normalize with scikit-learn. So this is a phenomenal article. I'll make sure it's in the resources section for you. But if you want to read through this for a bit more information on what scaling is, what the different kinds are, why you should do it. So here we go. Here's a great reason. Many machine learning algorithms perform better or converge faster when features are on a relatively similar scale and or close to normally distributed. Examples of such algorithm families include neural networks, which is what we're building. But we're going to see this. I don't want you, again, to just continually just learn from reading things. I want you to write code to see it for yourself. So let's jump into that. Enough talking, Daniel. All right, what's this first step? What should we do? We might import, we'll start again. We'll start fresh. So import pandas as PD, because I want you to be able to just come to this section in the notebook later on and just run it straight from here. Then we want to import matplotlib.lib.pyplot as PLT, and then import TensorFlow as TF. Wonderful. And then we'll read in the insurance data frame. So we go here, insurance equals pd.readcsv. We'll have to come back up and copy the URL, just the same URL we used as before. There we go. We're going to copy this one just to reinstantiate this data frame. That's all we're doing, so that we can start from scratch and see what pre-processing our data or normalizing our data does. Here we go. We'll make sure it's a string, and then we'll check insurance. Beautiful. All right, so we've discussed the concept of pre-processing data, normalization and standardization. We come back to the keynote. We've discussed the names of them, but now it's time we're going to get hands-on. We've reinstantiated our insurance data frame. In the next video, we're going to go through normalize the numerical features, and we'll also prepare the non-numerical features as well, and then we'll fit our neural network. So I'll see you there. Welcome back. In the last video, we discussed the concept of pre-processing data in terms of normalization and standardization. Now, we're going to get hands-on normalizing the numerical features of our insurance data frame here, and then we're going to build a neural network to learn on the features once they've been normalized. So let's see this in practice. Alrighty, how can we do this? So to do this, we're actually going to borrow a few classes from scikit-learn. So what I'll do is I'll code it up and talk through it as we go. You follow along as best we can, and then we'll discuss it once we've gone through it. So first of all, we're going to need, or actually, to prepare our data, we can borrow a few classes from scikit-learn. Wonderful. Okay, so from sklearn.compose, we're going to need make column transformer. Remember, you know how to look up the docstring of these things now, so you can see what these mean if you're not sure, but you could probably guess. Import, we're also going to need min max scaler, and I'm not pulling this name out of the air, one hot encoder. If we come back to our keynote, scale or normalization, we can use the min max scaler in scikit-learn. So we come back. Now what we're going to do is create a column transformer. This is very helpful. So why do you think it might be called column transformer? Well, if you've guessed, because we have columns here and we need to transform them in some way before passing them to our neural network, you'd be correct. But let's see it in action. Let's call it just CT for column transformer. We'll run make column transformer, and we might just run this cell first so that we can see what the docstring is for make column transformer. Here we go. Construct a column transformer from the given transformers. And we come here, transformer estimator, columns, string. Where's an example? Example, here we go. So make column transformer, standard scaler. Oh, where have we seen that one before? That's this, standard scaler. And what else was there? One hot encoder. All right, so we're actually going to need both of those, but instead of standard scaler, we're going to use min-max scaler, which is transform features by scaling each feature to a given range. So the default is between 0 and 1, which is what we want with normalization. So let's see this in action. We're going to pass it the columns or the column names that we need to normalize. So let's put a note here. Turn all values in these columns between 0 and 1. Now, how did we know this? It's because when we look at our data, when we explore our data, we've got age here, we've got BMI, and we've got children. These are the numerical columns. We don't need to scale this, our target variable, but we might want to scale our feature variables. And we know for the sex, smoker, and region columns, we're going to one hot encode them just as we've done before. So let's come down here. And now we need to make a one hot encoder. And we're going to set this parameter to the handle unknown equals ignore. So this just means if there's any columns that the one hot encoder doesn't know about, just ignore them. And then we're going to pass it the columns we want to one hot encode. Smoker and region. Wonderful. So have all the brackets correct? Yes, there we go. Beautiful. Now we've got our column transformer ready. So as we pass our data through this, it's going to get min-max scaled on these columns and one hot encoded on these columns. So now let's create our X and Y values because remember we just re-imported our data frame as a fresh. So X is going to be insurance.drop charges. And then we'll do that on the first axis. Y will be, what are we trying to predict? We're trying to predict charges. Beautiful. No typos there. And now, what do we want to do next? We've got our X and Y, but what do we want our model to learn on? Remember our 3 data sets? We want to train our model on some training data and evaluate it on some data it hasn't seen, in other words, test data. So the beautiful thing here is that we can use scikit-learns. Oh, we should put this up here, from sklearn dot model selection import train test split. So now let's build our train and test sets. So we want xtrain, xtest, ytrain, ytest equals train test split x, y. Test size equals 20% of a test data set. And the random state we're going to set to 42 so that the split happens exactly the same as you can scroll up before as we did before. Otherwise, it'll be random and we'll get different results. So now we're going to fit the column transformer to our training data. So the important thing here is that whenever you have some sort of column transformer, you want to fit it to your training data and then use that fit column transformer to transform your test data. Because otherwise, if you do that separately, remember the test data is data the model has never seen before. So it's basically data from the future. So if we're transforming our training data set with information from the test data set, it's like taking knowledge from the future and altering the data that we have now. So let's go here, ct.fit on xtrain. Now we want to transform training and test data with normalization, min-max scaler, and one-hot encoder. So let's go xtrain normal for normalized equals ct.transform. So now we're taking what we've learned from the training data and we're transforming it. We're normalizing the features and one-hot encoding the features that we've defined up here. And now we've got xtest normal equals ct transform xtest. Beautiful. So now we've been through a fair few steps here, but when we break it down, we've just created a column transformer with the minimax scaler and the one-hot encoder. We've turned our data into features and labels. We've split our data into training and test sets. We've fit the column transformer to the training data only, and then we've transformed our training and test data with normalization and one-hot encoding. Let's see what, oh, we got a typo here. Beautiful, that runs without errors. Now, we've normalized our data and one-hot encoded it. Let's check out what it looks like. What does our data look like now? So we want to go xtrain.lock. Let's look at the first one. Oh, sorry, we want to go, oh, well, that's what it originally was. So then if we go xtrain normal.lock. Oh no, maybe we just want the first one. Alrighty. So here's what we started with. Age is 19, sex is female, BMI 27.9, children, smoker, region. Now we've got a value here. I'm guessing that's the age. This must be the BMI. This must be the children. And now all of these other values are 1 or 0. Beautiful. So is that the same for another sample? And how about another sample? Wonderful. Well, what does the whole thing look like? Ah, it's all in numerical format. Now, what does that mean? Well, if you guessed, we can pass this to our neural network as all encoded data. You'd be 100% correct. So let's check the shapes. One more thing. Oh, we'll keep that sample there. And then we'll check the shapes of our data now. How has our shapes changed? So xtrain shape and xtrain normal.shape. Ah, okay. So you see our X train value had 1, 2, 3, 4, 5, 6 different columns here. Well, now, since we've normalized it as well as one and hot encoded it, we've actually added some extra columns here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alrighty, so it looks like that our data is ready to build and pass to a neural network model. So what we might do is, actually, I'll write a text cell. We'll write beautiful, because it is beautiful. Beautiful. Our data has been normalized and one hot encoded. Now let's build a neural network model on it and see how it goes. So the challenge for you is to now build a neural network model to fit on our normalized data. So you probably want to build one similar to the insurance model we built before. Just in the same way we've been doing it, build the model, compile the model, fit the model, and then evaluate it. So fit the model on the training data set, and then evaluate it on the test data set. So if you want to give that a try, go right ahead. But otherwise, we'll take care of that in the next video. Welcome back. Did you give it a shot? Did you try building a neural network to fit on our normalized data? If not, that's perfectly fine. That's what we're going to do in this video. So let's get started. We'll set the random seed so we can have as much reproducibility as possible. Let's set seed, 42. And now we're going to, step 1 is create the model. Now, if you scroll back up, you'll see that our best performing model is, or maybe you just remember, was insurance model 2. Now, if we get a summary of what that was, insurance model 2 dot summary, we're going to just reproduce the same model. Oh, another typo. But this time we're going to call it, so there we go, 3 layers, 1 dense of 100 units, 1 dense of 10 units, and the output layer of 1 unit. So let's reproduce this, and we'll make it insurance model 4 equals TF Keras sequential. And we'll come right to the start. We'll go TF Keras layers. We'll add the first hidden layer to our model with 100 hidden units. TF Keras layers dense 10 and TF Keras layers dense 1. There we go, we reproduced that. Now, what's the second step when we're creating our models? Step 2 is to compile the model. So we'll take insurance model 4 dot compile, and the loss function is going to be TF Keras losses.mae. And the optimizer is going to be TF Keras optimizers. We're going to use Atom because that's the same optimizer we use for model 2. And then we can go metrics equals MAE. Beautiful. Now, number 3, here's where the different part is going to be. So insurance model 2, we fit it on, if you scroll up, you can check it out, on unnormalized data. So we just fit it on X train only with 1 hot encoding, but not normalized. So to change the experiment, here's where our experiment, we put on our experimenter hat. When we're running these experiments, we're just changing one small thing at a time. So the thing that we're changing in this experiment, insurance model 4, is the data we're using. Everything else remains the same. X train normal, because we want to see, but it can still fit on the same labels. And we want to fit for the same amount of epochs. So we can still see, we only change one little parameter here, so we can see how that influences our model. Now you're ready? And go. Beautiful. Training is going to be nice and quick. All right, okay, MAE 3636. Now we're going to evaluate our insurance model trained on normalized data. So we got insurance model 4 dot evaluate. Let's get it on. Now we have to evaluate it on the same type of data it was trained on. So that's an important point too, is because we trained it on normalized data, we have to evaluate it on normalized data. Shift and enter. Insurance, I keep typing N before A. There we go. How did it go? Okay, 3438. Now, if we come back up to our insurance model 2, which was the best performing model so far, where was that? So there's insurance model 3. All right. So that didn't do too well on the test data set. Now, what we're after is insurance model 2. Oh, look at that. Evaluating the larger model. So if we copy this, let's copy this so we can compare our other model. If we were doing this properly, we might have saved the results of insurance model 2 to a variable, so we didn't have to go up and copy this. But let's make a code cell. So this is insurance model 2. Insurance model 2 results. Look at that. What a reduction. So that's 5,000 MAE. Just by normalizing our data, we've gone from 5,000 MAE to 3,500 MAE. That's incredible. That's a reduction of like 30% or so. So now I hope you're starting to see the benefits of all of the different hyperparameters we can tune with our model. So not only can we tweak how we construct our models, how we compile them, how we fit them, we can also tweak the data that we pass it to them. So if we come back and look at our keynote, this is what we've done. We've done the scaling type. All we did was we convert the values or the target features that we wanted to convert to be between 0 and 1. That's all we changed. And we did that with about 10 lines of code here. And those 10 lines of code saw a reduction in error of about 30%. How cool is that? So that's the experimenter mentality that I want you to start developing throughout the rest of this course, is that the first result you get when you build a neural network model is actually, it's definitely not your last result, because there are lots of different things that we can tweak. We can tweak the model, we can tweak the data. We're going to have a lot more experience with this going forward, but that's one of the main benefits of normalization, is we see a faster convergence time. What that means is that our model gets to a better result. I mean, if we trained insurance model 2 for longer, say for 200 epochs, it might have reached this error rate here. But when we normalize our features, our models tend to converge faster. In other words, they get better results faster in less epochs. So, again, normalizing data doesn't guarantee improved results, but it's something worth trying because of how easy it is to implement. And in fact, in a lot of our pre-processing code that we do going forward, normalization will be built in, such as when we're dealing with images. Alrighty, so I think we have covered well and truly enough for neural network regression with TensorFlow. Have a look at this. Look how far you've come. You should be incredibly proud. We started by creating data to view and fit. We dealt with input and output shapes. We went through our steps in modeling with TensorFlow. If we come back, this big boy here, look at that. We went through all of these different steps. How cool is that? Now, we improved our models. We evaluated our models through visualization and evaluation metrics. We've run a whole bunch of experiments. We've loaded and saved our models. And we've even gone through a larger example from an open source data set. So give yourself a pat in the back. I've set up some exercises and extracurriculum activities to go along if you want to test your skills even further. I really encourage you to try out the exercises before looking at the solutions that come along with them. But otherwise, go back through all of the concepts. If there was something you didn't really understand, practice it, write a bunch more code, get a few things wrong, see what works, see what doesn't, and I will see you in the next section. Neural network classification with TensorFlow. Now, before we get into anything, what we're going to cover or any code at all, I need to stress something. And that's, where can you get help? I'm going to be writing a bunch of code. We're going to be writing code together. So make sure you follow along with the code if you can. Remember our motto, if in doubt, run the code. Don't forget to try it for yourself. If you need the doc string, which is a bunch of information about the functions that we're going to be using. If you're using Google Colab, you can press Shift, Command plus Space, or if you're on Windows, this might be Control. If you're using Jupyter Notebook, it's probably going to be Shift and Tab. If you're still stuck, you can search for whatever problem you're having. And we're going to get a lot of practice searching for our problems as well, because that's what I want to stress. As much as we can teach in this course, you're still going to have to develop the skill of being able to search for answers to your own problems. Now, if you do search for it, you'll probably come across resources such as Stack Overflow, or probably more importantly, the TensorFlow documentation, since we're going to be writing a lot of TensorFlow code. And then after you've searched for it, try again. Rewrite the code if you have to. Look at the examples in the TensorFlow documentation and copy them out by hand and try them in your own notebook. And then finally, this is probably the most important out of all of these steps, is if you're still stuck, ask a question. Don't forget the Discord chat, and that means including those dumb questions that you think you have. All right? The person who asks the most dumb questions gets smartest the fastest. Oh, and actually, I want to add one more to this list, and that's the course GitHub. So if we come to here, GitHub, this is Mr. D. Burke, that's me, TensorFlow Deep Learning. This will have all the materials related to the course you're currently going through. I'll leave a link. At the moment, it's still a work in progress, but by the time you go through this video, it'll have a bunch more stuff and everything you need. Now, every notebook and concept we go through has a ground truth notebook. So, for this one, 02, Neural Network Classification and TensorFlow, this is the information we're going to go through. In the videos, we're going to be writing all of this code out. However, the notebooks here, so this one in the GitHub, have a lot more text around the code that we're writing. So if you want a more text-based explanation to go along with the videos and along with the code, so say in the video we just write this code, if you want all this annotation around it, be sure to check out the TensorFlow Deep Learning GitHub, and that'll have all the information you need. So without any further ado, let's get back to our keynote. And since we're covering neural network classification, you're probably asking yourself, what is a classification problem? Well, let's have a look at some example classification problems. The first one is binary classification. Is something one thing or another? Now, an example of this would be asking the question, is this email spam or not spam? That's actually probably a trend you'll see in binary classification. Is this thing something or not something? So here, we've got clearly a nice email to my email there, daniel@mrdburke.com. Hey Daniel, this deep learning course is incredible. I can't wait to use what I've learned. Oh, thank you so much. That's a beautiful email. I definitely want to see that in my inbox. So we might train a machine learning model or a neural network to classify this text as not spam. And then if I have this email here, which is, again, to my email, daniel@mrdburke.com. Hey Daniel, congratulations, oh, that's a 1. A bit of a typo there. You win a very large sum of money. As much as I'd like that large sum of money, that's probably spam, and I don't want to see that in my inbox. So that's binary classification. Now, another very common classification problem is multi-class classification. This is where you'll have a question such as, is this a photo of sushi, steak, or pizza? So we have a photo of sushi, we have a photo of a beautiful, delicious steak, and then a delicious pizza. Now, multi-class, as you might have guessed, is more than one thing or another. Now, we've got 3 classes here, sushi, steak, pizza, but in multi-class classification, we could have 100 different classes or 1,000 different classes, but the principle would still remain. Is this a photo of, say we had 100 different foods, maybe we added over here a sandwich. So the principle would still remain. There's multiple different things that these photos could be of. So multi-class classification not only relates to different photos of food, it could be different photos of cars, it could be different photos of animals, anything you could imagine. And finally, another very common classification problem would be if you are asking, what tags should this article have? So here we have the deep learning article from Wikipedia. Now, maybe you want to, if you're Wikipedia, you want to sort your articles, because you have millions of them, into different categories. And so just labeling it with one category, such as deep learning, may not be enough. You want to relate it to other things, such as machine learning or representation learning, or artificial intelligence. So in this case, multi-label classification. Now, these two are going to be pretty confusing to begin with. You just need to figure out a couple of example problems to sort of start to understand them. But I know when I first started deep learning, I often got multi-class classification and multi-label classification mixed up. But the easiest way, or the way I remember multi-label classification, is that there's multiple label options per sample. That means that this one sample, this one article here, could have 3 different tags, or it could have 5 different tags. Whereas in these photo examples in multi-class classification, we only want one label per sample. So we have one photo, and the one label would be sushi. One photo, one label would be steak, and so on for pizza. Whereas in multi-label classification, we have one sample and multiple labels. So now that we've had a look at some of the most common classification problems you're going to come up against, binary classification, multi-class classification, and multi-label classification, let's have a look at the things we're going to cover, or specifically the things we're going to write code for. So here's what we're going to cover, broadly. Now I say broadly because these are just subheadings. What really matters is what we actually write code for. So we're going to look at the architecture of a neural network classification model. We're going to see the input shapes and output shapes of a classification model. In other words, the features and labels. We're going to look at creating custom data to view and fit. We're going to go through the steps in modeling, such as creating a model, compiling a model, fitting a model, and evaluating a model. We're going to see what different classification evaluation methods we have. And then finally, once we've trained some models, we're going to look at how we can save them and load them. And how are we going to do that? Well, we've seen this before, but we'll see it again. We're going to be cooks, not chemists. Cooks are very experimental. They try a whole bunch of different things, and they might measure something a little bit, but they're also going to just, if a recipe isn't going exactly how they want it, well, they're going to improvise. So that's what we're going to be doing. We're going to be cooking up lots of code. So now we've covered some example classification problems and what we're going to cover. In the next video, let's check out what the inputs and outputs of a classification model might look like. So, let's say we're working on a classification problem. And we saw this before, the idea of taking some photos, and then perhaps we're building an app that we want to be able to take a photo of whatever food we're eating and classify it as sushi, steak, or pizza. That's the app that we're building. What might our inputs and outputs look like? Well, we've kind of already got them here. Our inputs are going to be some kind of image of food. And then our ideal output, something over here, will be, if we took a photo of this one, we want it to be sushi. And if we took a photo of this steak, we want it to be steak. And then if we took a photo of pizza, pass it through our app, the ideal output would be pizza. Now, what might this look like in practice? So, all right, well, here's our little scenario here. This is our machine learning algorithm that we might build, or deep learning algorithm. And we've already discussed what our inputs are and what our ideal outputs are. But what's the rule that we have to, before we can pass our inputs to our machine learning algorithm, or better yet, what does our machine learning algorithm like to look at? Can it understand photos straight away? Like if we just took a photo and just said, hey, machine learning algorithm, tell us what's in this photo. Will it be able to do that? Well, if you remember from a previous section, what do we have to do to our inputs before we pass them to our machine learning algorithms? Oh, maybe this is a little inkling. So if you're not sure, that's perfectly fine. But what this is so if we have a photo, let's say we already know what the width is and what the height is. So it's 224 by 224. So this is a square image. Now, what are we moving towards? We're starting to numerically encode what an image is. So we're starting to break it down from being just an image to being, okay, this is a 224 by 224 image. All right, we know a little bit more information about our image. So we know the width, we know the height. Oh, and what's C? We might know the color channels. So that's 3. So C equals color channels, red, green, and blue. So we might know that some combination of red, green, and blue pixels in 224 by 224, some combination of those different color values are going to give us this image of sushi. And the same thing for steak, and the same thing for pizza. Now, these width and height are arbitrary, but very often you'll change your numerical inputs of a machine learning model to have all of the same width and all the same height when you're dealing with images. So what might we do before we pass these inputs directly to our machine learning algorithm? Well, we're going to turn them into a tensor. In other words, a numerical encoding. Now here, we've got normalized pixel values. So that means we've changed them to be whatever they were in terms of red, green, and blue, to be some value between 0 and 1. We're going to see this very hands-on in upcoming videos, so don't worry if this isn't making sense. The concept here is that we have images and we have to turn them into numbers in some way, shape, or form before we can pass them to our machine learning algorithm. And then our machine learning algorithm often already exists if we're using something like transfer learning. If not, we can build our own custom one. And then we pass it through. The machine learning algorithm is going to learn patterns in the data and then create some prediction outputs. So let's see here. What have we got? Okay, we've got another tensor, and it seems that the highest value here is highlighted for sushi. All right. But we get 0.00 for steak and 0.03 for pizza. Is that the first image? So that would be correct. Okay, that's great. But then this second image, the one of the steak, the highest value, it predicted sushi. And then these two values are lower for steak and pizza. So that would be wrong. This one, okay. So 1 out of 2, not too bad. And then this final one here, say this is for the pizza image. Same process again, turn it into numbers, pass it to our machine learning algorithm. And then it's got a predicted output here of 0.03, 0.07 for steak, and then 0.09 for pizza. So the highest values for pizza. And so that would be correct. Wonderful. Now, how does it generate these? Well, if we have a look, what are the actual outputs that we were looking for? In our case, we're building an application to classify different images of food. We take a photo of food, we run it through our machine learning algorithm, and then the ideal output is, for this photo is sushi, this photo is steak, and this photo is pizza. So, if we wanted our machine learning algorithm to be able to create predicted outputs like this, perhaps we can show it lots of different examples of images and their ideal output. Okay, so this is the premise of neural network or machine learning classification. This is our inputs over here. We numerically encode them, pass them to our machine learning algorithm, and then have some sort of output. All right. So the example we've seen here is for multi-class classification because there's one or more, each image or each sample can be one or another class. However, this premise of taking some sort of samples, numerically encoding them, passing them to a machine learning algorithm, and then have some sort of output, goes for all different types of classification inputs and outputs. So now we're familiar with the high-level overview of what a classification inputs and outputs will be. Let's have a look at what the shape of these tensors would be, because that's another very important point, as we'll see in practice later on. But before we do so, I want you to have a think about, if we've got these inputs, what might the shape of our input tensor be? And if we've got these outputs, or these ones here, what might the output shape of our output tensor look like? Have a think about that, and we'll cover that in the next video. Welcome back. In the last video, we checked out an example multi-class classification problem, or in other words, the inputs and outputs of what that type of problem may look like. So we had some images here, food images, and we wanted to take a photo of them and classify them as what's in that image. So in our case, we had sushi, steak, and pizza. We learned that no matter what classification inputs we have to numerically encode them in some way. So for an image, we grabbed the pixel values. So we learned that the width was 224, the height was 224, and there was 3 different color channels, red, green, and blue, and we figured out that we can turn those into a tensor and pass that to our machine learning algorithm. It's going to figure out some patterns in these input tensor or in the input images, and then create some predicted output that's based on looking at lots of actual samples of image to label pairs. So knowing that our inputs are in the form of a tensor and the outputs are in the form of a tensor, let's now have a look at what the input and output shapes of those tensors are, which is a very important concept. Because we're working in TensorFlow, all of our data is going to be contained within tensors. Inputs and outputs of our neural networks, of our deep learning models, of our machine learning models are all in tensors. And if they're the wrong shape, well, we run into errors. So this is for an image classification example. We're continuing off with what we just saw. We have our little setup here. Inputs, machine learning algorithm, outputs. We have our image of food. In this case, is just the sushi one. And we know that the width is 224 and the height is 224. And there's 3 color channels, red, green, and blue. So what we might do is numerically encode this, pass it as an input to our machine learning algorithm, and it's going to output some kind of prediction probability. We haven't covered this, but we will see this in code later on. This is just more so the concept. Now, the reason why there are 3 options here is because we are building a multi-class classification image classifier, where the output could be sushi, steak, or pizza. And in this case, our machine learning algorithm has got this one correct because the highest value is for sushi. And that's what the input image is. Now, let's check out what or how our image would get represented as a tensor. So here we go. These might be the dimensions of our input tensor. Batch size, something we haven't covered yet, but that's all right. We'll see that coming up. Width, height, color channels. We have covered these. So the width here is 224. The height here is 224. And the color channels would be 3 for red, green, and blue. Now, the shape of this tensor will be, for batch size, might be none, 224, 224, 3. Do you see how the width value goes into here, the height value goes into here, and the color channels go to here? Or we might have a shape of 32 for the batch size, 224 for the width, 224 for the height, and 3 for the color channels. Now I've set 32 here because 32 is a very common batch size. All you need to know for now is that oftentimes when we're training a machine learning algorithm, depending on how much data we're working with and depending on the size of the computing chip that we're working with, it may only have enough memory to look at 32 samples at one time. So say we're working with 10,000 images, which is very common in image classification. Our machine learning algorithm may only look at 32 images at a time so that it doesn't run out of memory. And again, the reason why it's none or 32, 32 is very common. I think it's actually the default batch size in TensorFlow, but none is because this could be an arbitrary number. And it's important here that the width of this image isn't set at 224 and the height isn't set at 224. But again, these are very common values you're going to come across. So that might be what our input tensor shape looks like for a single image. Or if we have a batch of 32 images, it might be of this shape. And then if we have a look at our output, the shape of this might be 3 because we're dealing with multi-class classification and we have 3 potential classes. So that's the shape of this output tensor. Now, of course, this is for our image classification example. However, these shapes will vary depending on the problem you're working on. So say what if we had 10 different types of food here? What do you think the output shape would be? Well, it might be 10. And say this image was 300 by 300. What might change here? Well, the width and the height might change to 300 and 300. So we're going to get very hands-on with this going forward, but this is just to demonstrate conceptually what we have to do for our classification problems to work on them with deep learning and machine learning algorithms. We have to take our data, numerically encode it into some way, which is typically represented as a tensor, and because we're using TensorFlow, it will always be a tensor. And then the same with the output. Depending on what outputs we have to define them as some sort of tensor, and they will typically have a shape dealing with the number of classes. If you're working on multi-class classification, that is, the output shape will have the same number, or will be the same number as the number of classes we have. But again, this is just a conceptual overview. It'll start to make a bit more sense once we start to build classification neural networks. And speaking of which, let's have a look at that in the next video, what the typical architecture of a classification neural network looks like. Welcome back. In the last video, we had a look at what the input and output shapes of an image classification example might look like. And remember, this is specifically for an image classification example. These may change depending on the problem you're working on. So say we were working on text classification. Your input shape may differ to be the number of words in a string. So it may be 32 and then 100 for 100 words, and it won't have these dimensions over here. It'll just be one number for each word in that string. And then the same over here. Say we would just wanted to classify an email as spam or not spam. We may have an output shape of 2. Again, lots of practice coming up, but just keep in mind, one of the big things for classification problems is defining the input-output shapes of our machine learning or deep learning algorithms. So now, speaking of those, let's have a look at what the architecture of a classification model might look like. We've got a little spoiler alert here. Here's some TensorFlow code. We've been very familiar with this in the regression section. However, we might notice a few different things. Oh, we've got input layer. All right. We've got activation. We haven't seen much of that. We've got another activation here, softmax. All right. What else is different? We've got loss. Okay. So we're familiar with these steps. 1, 2, 3, 4. The main differences you might see here is the loss function and the input shape and the activation. We haven't been hands-on with those just yet, but throughout the classification section, as you might have guessed, we definitely are going to be. So now, it's important to note that this is a typical architecture of a classification model, and we're going to building lots of these. So although I'm giving you sort of a guideline as to what these architectures may look like, they definitely vary depending on the problem we're working on. However, this is pretty universal. And again, this is adapted from page 295 of the Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow book by Aurélien Guérin. Highly recommended that book. It'll be in the extra curriculum section of this course. So let's take a look at what's going on here. We have hyperparameters, and remember, a hyperparameter is something that we can adjust ourselves as developers. And we might have a binary classification problem and a multi-class classification problem. Now, note here, we haven't got multi-label classification. However, multi-label classification architecture is often very similar to a multi-class classification. So, let's start with the input layer shape. If we go here, and all of these colors are going to activate for me automatically, aren't they? But that's all right, we'll step through it one by one. Input layer shape, we have here, TF Keras input. So here's where we're defining the input layer shape. Do you remember in just the previous example we looked at before, it might be the same number of features, e.g. 5 for age, sex, height, weight, smoking status in a heart disease classification problem. But we looked at an image classification problem. So here we might have the input shape of a particular image might be width, height, number of color channels. So that's what our image looks like in tensor form. Again, this shape will change depending on the problem you're working on. Now for multi-class classification, it's going to be the same thing as binary class classification. Now hidden layers, again, this is plural on purpose. We've got one here, and this is problem specific, what you set this to. The minimum is going to be 1, the maximum is unlimited. So I think we're actually going to be working with a neural network with over 100 layers. That might be in this section or a later on section, but this one just has one hidden layer there. And for multi-class classification, we can look at the same value here. It can be 1 or up to unlimited. Neurons per hidden layer. That's this green value here. Problem specific, generally 10 to 100. Again, this can wildly vary depending on what you're working on. In our case, we've set 100 here to the hidden layer. And for multi-class classification, we've got same as binary classification. Now the output layer shape. For binary classification, it's going to be 1. So remember, binary classification is something one thing or another? Is this email spam or not spam? So we want the output layer shape to be 1. And multi-class classification is going to be 1 per class, e.g. 3 for food, person, or dog photo, if we were working on an image classification problem to decide whether a photo was of food, of a person, or of a dog. And that's the value we've put here, 3. So in our case, this input shape might actually work for this problem here. This output shape. But the input shape would also work because it could potentially, if these images, so the images of food, of a person or a dog, were 224 pixels wide, 224 pixels high, and had 3 different color channels. Once we'd turn them into tensors, of course. Now we have here the hidden activation. So this is the hidden layers. So the activation function that we have within the hidden layer. So it's often defined with the activation parameter. Now it's usually ReLU, which is rectified linear unit. We haven't seen that before, but if you want to go ahead and do a little bit of research before we get into coding, feel free to look up ReLU. And again, same for multi-class classification. We're going to use now again, there are multiple different hidden activation functions, but I say usually ReLU because that's what you're going to see very often, and that's what we're going to be using throughout the course. Now, output activation. This is the activation function in the output layer. Again, a concept we haven't really covered so far, but I'm just making you aware of what the names of these things are. So for binary classification, we're probably going to be using a sigmoid activation for our final layer. And for a multi-class classification problem, we're probably going to be using a softmax activation, which is what we've got here. All right, so this architecture looks like it's for multi-class classification. Now, loss function. Across the board, we're going to be using cross entropy, which is a loss function for classification problems. Now, for binary classification, we're going to be using binary cross entropy in TensorFlow. And for multi-class classification, we're going to be using categorical cross entropy in TensorFlow. So it looks like here, when we compile our model and define the loss function, we've used TF Kera's losses categorical cross entropy, which makes sense because we discussed before that this is a multi-class classification architecture. And as for the optimizer, we're going to use old faithful stochastic gradient descent, or another old faithful is Atom. So actually, I think we might test out both of these, but I think we're probably going to be sticking with Atom because Atom is safe. And then we go here, multi-class classification, same as binary classification. All right. So that's a typical architecture of a classification model. Again, a lot of things here that we haven't necessarily covered, but we are going to be getting hands-on building a lot of these. And I think that's what we've got here. Yeah, we're going to be building lots of these bad boys. And the reason you might be wondering why I said Atom is safe, I want to reveal that. So let's go here. Andre, here's another external resource. Neural network recipe. I'll put this in the extra curriculum. A recipe for training neural networks. So this is by Andre Karpathy. If we go here, Atom. A few tips and tricks for this stage. Atom is safe. In the early stages of setting baselines, I like to use Atom. He's talking about the Atom optimizer. With a learning rate of this, Atom's learning rate is actually very good in TensorFlow. It's default 1. In my experience, Atom is much more forgiving to hyperparameters, including a bad learning rate. For convnets, a well-tuned stochastic gradient descent will almost always slightly outperform Atom. So again, a lot of things here you might not be aware of, but just know Andre Karpathy is saying Atom is safe, and if you're wondering who Andre Karpathy is, let's go to About, see my website. I am the Senior Director of AI at Tesla. So Andre knows his stuff about deep neural nets. So if Andre says Atom is safe, we're going to trust him. But anyway, actually, let's be skeptics. let's not trust Andre and let's test it out for ourselves. So in the upcoming videos, we're going to get... Oh, actually, I had a little demo of what was happening here. So here's our inputs. They get encoded into tensors of this shape. And then here's our outputs. So that completes that slide. But with that being said, we've talked enough. Let's code. Now that we've looked at what a classification problem is, what some tensor input and output shapes might look like, let's get hands-on and start to code some classification code. We're going to start a new notebook at Colab. Wait for this to load up. Beautiful. Now I'm going to call this one O2 neural network classification with TensorFlow. And I'm going to add the video tag so that you know, once you see this notebook in the GitHub, that this notebook was made during the recording of videos. Remember, we've got in the GitHub, the ground truth version of this notebook doesn't have the video tag on the end here. But we'll get out of that. So let's write here, introduction to neural network classification with TensorFlow. So in this notebook, we're going to learn how to write neural networks for classification problems. And remember, what's the definition of a classification problem? A classification problem is where you try to classify something as one thing or another. And there's a few types of classification. You've got binary classification, multi-class classification, and multi-label classification. And we've got here a few types of classification problems. Now, we'll turn this into Markdown. I'm going to press Command MM. You might press Control MM if you're on Windows. So, we've got a little intro here. Now, the first thing we might have to do is, before we can write any code, is we need some data. So how about we write a title here, creating data to view and fit. Now, there's a lot of toy classification data sets out there, but I always like creating our own and getting a model to work on our simple data set before moving on to an actual problem. So it's like a rehearsal experiment before our actual experiments. How about to make some data, we can go from sklearn.datasets, import make circles, and then we'll go here. We want to make 1,000 examples. So we want 1,000 different samples of data, and we can create circles. Oops. And samples equals 1,000. And then if we should go down to here, create circles, x, y equals make circles, and samples. Again, you could change this to 10,000 if you wanted to, or 100. I'm going to stick with 1,000. That's a good number. And samples, noise can be 0.03, and random state can be 42 if you want to make this reproducible, so we have the same data. Now, you might be wondering, Daniel, we've never used make circles before. And you'd be 100% correct. This is the first time we've used this in the whole course. But how do you get help on something if you weren't sure? We want to press Command, Shift, Space. Def make circles. So make a large circle containing a smaller circle in 2D. A simple toy dataset to visualize clustering and classification algorithms. Beautiful. So if we really wanted to figure out what this is how to make example classification data with sklearn. There we go, an introduction to machine learning with scikit-learn, examples. So we've got a few options there. I've just chosen, that's basically what I did when I found out about this make circles function. And there's probably a way to do that in TensorFlow. I'm not quite sure if it's as quick as this one, but if you want to give it a try, once you see what this data looks like, feel free. So now let's check out the features, which is under the X namespace, usually a capital X. Okay, so we have an array here, and let's check out the labels. Check the labels. All right, ones and zeros. So we've got two options here. I'm guessing one of these samples here, so this is a sample, has this label, number 1. And another sample further along here, say this one, has this label 0. We might just make this a bit smaller. I'll check the labels, that's what we want there. So if we have two label options and we're working on a classification problem, which one of these three are we working on? Is it binary? Is it multi-class? Or is it multi-label? Well, it's not multi-label because each one of these has one label. So each sample has one label. And it's not multi-class because there's only 1 or 0. So this is a binary class classification problem. But if we're looking at our data like this, I mean, I could look at this. I've used this before, so I kind of know what this means. But if you're looking at this for the first time, it might not make sense. So what's our Data Explorer's motto? Come back to the keynote. The machine learning, or even the Machine Learning Explorer's motto. Visualize, visualize, visualize. What's the first thing we should visualize? The data. We could visualize the model, the training, predictions. And it's a good idea to visualize these as often as possible. So let's see how we might visualize our data. Let's write ourselves a little note. Our data is a little hard to understand right now. Let's visualize it. So to get it into a structured format, I'm going to import pandas as PD. Then I'm going to turn it into a data frame called circles. PD.dataframe. And I'm going to label it x0 for this element here, or this sample here. And that can be x, all of the items in the 0th axis. And then x1 can be x, we want all of the items in the first axis. There we go. And then we want the label column to be y. There we go. And let's look at our circles data frame. Typo there, of course. Circles. Beautiful. Okay. So now this is a little bit easier to understand as it is. We've got x0, x1. So we have two features per label. And so this coordinate 0.754246 and 0.231,481 has the label of 1, and so on, times 1,000 because we set n samples to 1,000. Now this is still a little hard to understand. I wonder if we can visualize this with a plot. Let's try that out. Visualize with a plot. So how might we do that? Import matplotlib. I like to visualize as much as possible before I start writing neural network code. plt.scatter. We want a scatter plot. Scatter plot's a very good plot. We want to just plot this. And the color can equal y. And the CMap can equal, this is just the color layout. I want it just to be red, yellow, blue. I think that should do. Let's have a look. Oh, look at that. Now, so, seeing this, if we read the doc string of make circles, has it done what it says it's going to do? Make a large circle containing a smaller circle in 2D. I think it's done that. We have a large circle and a smaller circle. Now, from this plot, can you tell what type of model we're going to build? It's okay if you can't, but I just guess. Like, what are we trying to do here? What would we try to do? I'm giving you a little hint here by running my pointer in between the two circles. How about we build one to classify red or blue dots? So in other words, we want our model to potentially draw a line right through the middle of these two. So if we were trying to predict on another 100 rows and we had values like this, would they be a 0 or a 1? Would they be red or blue? Now, I want you to think about, before we go ahead, this is just a conceptual thing. What is the difference between the data we're looking at here and the data we've looked at in our regression notebook? So if we start a new tab, what is a regression problem? And then if we went to images, what's the difference between this data here and this data here? So have a think about that. Just look at this, like Google regression problem, check out the images, and just have a think. What's the major difference between our two types of data here? And one more thing before pushing forward, so that's your challenge, just to compare these two types of data. I want you to have a look at TensorFlow Playground. Oh, .org, not .com. Here we go. Tinker with a neural network right here in your browser. Don't worry, you can't break it. We promise. So again, we've got a little few options here over what data set we want to use. And what's this one look like? I mean, we've got a few. Watch them change over here. We've got this one. What's the similarities between this data set and this data set? So your two exercises before the next video is to compare this one here. You might have already done that because we've talked about it enough. And then the other one is to spend 10 minutes at playground.tensorflow.org playing around with all the different parameters here. Try changing the learning rate, the activation, the regularization. Doesn't matter if you're not sure what these things are. Press play, change the number of hidden layers here, change the number of neurons, and see what happens with this data set here. So give that a try, and I'll see you back here in the next video. How'd you go? Did you play around with the neural network playground? I've just added a little exercise here with this hammer and spanner emoji. If you ever see that throughout the course, that's an exercise. So before pushing forward, spend 10 minutes playing around with the playground tensorflow.org, building and running different neural networks. See what happens when you change the different hyperparameters. So if you haven't done that yet, give that a try and then continue the video. But otherwise, we've created some data, we've visualized it. Now, what's another important point is the input and output shapes of our neural network. So let's inspect our data. So check the shapes of our features and labels. So what's our features shape and our labels shape? Wonderful. So we have 1,000 samples of X and 1,000 samples of Y, and X has a shape of 2 because there's 2 samples, whereas Y is just because there's one output. These are scalars, so they don't have a second dimension here. They're just one value. All right. So if we wanted to check how many samples we're working with, is just len X, len Y. And if we want to view the first example of features and labels. So again, we're just becoming one with the data here. We're really just familiarizing ourselves with what we're trying to do. We've already seen a few of these things, but just for completeness, we're putting this here. So, okay, we've got 2. Here's what we're trying to do. We're trying to take this point, feed it to our neural network, and generate an output, something like this. And let's say, can we get another one with a 0 label? Are we going to get a 0 label? Nope. I believe the 5th one may have been. No. All right. So some of these values here for X have a label of 0. That's all you have to know for that. Now, we've checked the input and output shapes. What might be the steps or the next steps? So steps in modeling. We've practiced this with our regression problem. So now that we know the input and output shapes, how might we build a neural network to classify whether something is a blue dot or a red dot? So how about we go back to our keynote here and steps in modeling with TensorFlow. We reveal our beautiful, colorful picture. Step 1 is get data ready, turn it into tensors. Well, we kind of have that, except they're in NumPy arrays at the moment. But remember, NumPy arrays work beautifully with TensorFlow. So we'll say that we've finished this one. Now we have to build or pick a pre-trained model to suit our problem. Well, in our case, we're going to build a model. So we have step 1, create a model specified to your problem. We might have to define the input shape here, or sometimes Keras layers can automatically infer the input shape. Then we might have a hidden layer and an output layer. What would our output layer shape here be? If we come back, we only want to predict whether it's one thing or another. If you remember back to the slide where we talked about the typical architecture of a classification problem, that may give you a hint because we're working with binary classification. Then we want to compile the model. That's step 2. I nearly said fit the model, but we have to compile it after we create it. Remember step 2, Daniel, come on. Now, if we're working on binary classification, what might our loss function be? What optimizer could we use? What metrics could we use? And then once we fit the model, okay, that seems like we've got that set up. We've got X and Y. Well, we haven't got a training data set actually, have we? Or a testing data set. We might just stick with X and Y for now. All right, so now we've got the steps here, 1, 2, 3, 4. I'm going to issue another challenge. We've got X and Y. See if you can create a model with what we've learned so far. Refer back to the slide where we talked about the architecture of a classification model and write some neural network code with TensorFlow. Give it a go, and I'll come back in the next video and we'll write a neural network classification model together. So in the last video, we checked out what the input and output shapes of our data may be. And we also had a brief overview of what the steps in modeling with TensorFlow are. So how about we start to implement those? So remember, the steps in modeling, number 1, or the steps in modeling with TensorFlow are typically 1, create or import a model, 2, compile the model, and 3, fit the model. And then the 4th one is evaluate the model, etc. 5 is we usually here will tweak, 6, evaluate, etc., etc. Tweak, evaluate, tweak, evaluate, tweak, evaluate. But let's focus on these first 3. We'll get these first 3 done for our classification problem. So how about we start? Set the random seed, tf.random set seed. Now what's the simplest model we could start with? How about we just start with 1 hidden layer. We'll go create the model using the sequential API. So we go model 1 equals tf Keras sequential, and then we'll add a single dense layer. Wonderful. And then what's step 2 after we create a model? We have to compile the model. So model 1 equals compile. Here's where it's going to be different from the regression models that we've built. And now before I write the code, I want you to refer back to this slide here. The typical architecture of a classification model. Where are we up to? Well, we're compiling a model. And we have to define the loss function and the optimizer. So if we look back at what we're working on, what are we working with? Are we working with binary classification or multi-class classification? Come back to our problem. What does it look like? Red or blue dots? So it is binary classification. So what might our loss function be? Before I write it in here, I'd like you to give it a try. Have a look at this and see what it might be. Did you give it a go? If not, that's all right. Let's write it down. Loss equals tf Keras losses dot binary. Is this going to autocomplete for us? Cross entropy. I believe it might be capital E, but we'll find out in a sec. It'll error for us. Now the optimizer. What optimizer do you want to use? TF Keras optimizers. We come back to our typical architecture of a classification model. We can use SGD or Atom, or really there's actually a plethora of optimizers we could use, but these 2 are the most common you'll see in practice. We'll start with SGD. And the metrics is going to be, we haven't looked at classification metrics yet, but we'll get very familiar with them. Actually, what would you do if you wanted to know different classification metrics. I put accuracy here. That's a bit of a spoiler. But let's go how to evaluate a classification model. Here we go, evaluating a classification model. What does this tell us? Richie NG. Oh, look at this. Topics. Review of model evaluation procedures, model evaluation metrics. Okay. Model evaluation metrics. Boom, classification. Classification accuracy. There are many more metrics and we will discuss them today. Classification accuracy. All right, beautiful. So then we got a few more options. We could keep going through that if we wanted, but we're just going to stick with accuracy for now. And accuracy is just basically out of 100 examples, how many did our model get right? So what percentage? And now if we go here, and we want to, well, step 3, fit the model. So we have model1.fit, we have X and Y, and we're going to fit for maybe just 5 epochs. So we've got the first 3 steps here. And all we've done is we've just followed this. The architecture of a classification model. We've just implemented this in TensorFlow code. So we're ready to run this. Hopefully there's no errors. 3, 2, 1. Oh, TF is not defined. That would help if we imported TensorFlow. Did you catch that? Let's write some code here. We'll get rid of this. We want to import TensorFlow. Can't write TensorFlow code without TensorFlow. Import TensorFlow as TF and check our version. By the time you watch this, your version might be higher than mine. Right now, I'm running 2.3.0. As long as you've got 2 point something, all the code should work in here. And let's see if this runs. We got this wrong. So, what is it? Tab. We want, is this going to autocomplete for me? So maybe it's just a little e, and I think this is on the end. There we go. Fits nice and quick because we're only working with 1,000 samples, but what's our accuracy? 48%. This is percentage, by the way, because we've set up accuracy here. So that's saying that on average, out of 100 examples, our model only gets 48 right. Now, what does that tell you? If we're working with a binary classification problem, so we're trying to predict whether something is one thing or the other, basically heads or tails, and our model is only 48% accurate, it's basically guessing. So it's just going up here. It's looking, we have red or blue, and 48% is basically 50%. So it's just going red, blue, red, blue, red, blue, red, blue, red, blue, and you'd get about 50% correct. Well, that's not very good. How might we improve it? What are some steps to improve our model? I got an idea. How about we train it for longer? So let's try and improve our model by training for longer. So we come here, model1.fit. We can just take it straight away. And epochs equals, let's do another 200. And this time we'll turn verbose to 0. So 200 epochs should be enough for our model to figure out the patterns in our data. We've only trained for 5. Let's really step it up. Model1.evaluate X and Y. Maybe you're going to catch what I'm doing wrong here. We'll reveal that after. But if you have a look at what we're doing here, fit and evaluate. I'm doing a cardinal sin right now, but that's all right. This is just to exemplify what's going on. Let's see what happens. So it took a little while longer to fit because we're training for 200 epochs instead of 5, but we ran evaluate and now we have loss. So the loss is 6935 and the accuracy is 5 or 50. So 0.5 times that by 100, that's 50. Only 50% accuracy and we trained for 200 epochs. What is happening? Okay, I know how we can really step things up. What if we added another layer and trained for longer? Yeah, that's a great idea. Our model is performing as if it's guessing right now. Let's write that down. Since we're working on a binary classification problem and our model is getting around 50% accuracy, it's performing as if it's guessing. So let's step things up a notch and add an extra layer. Yeah, that worked in our regression problem. It should surely work here. So we'll set the random seed. tf.random.setSeed. And we'll go to step 1, create a model, this time with 2 layers. Model 2 equals tf Keras sequential. Open up the brackets there, square brackets and curly brackets. tf Keras layers dense. Woohoo! This data set ain't gonna know what hit it. Binary classification, 2 different types of labels, 2 layers. And now, what do? After we create a model, we have to compile the model. I'm going to go model2.compile. What's our loss function? tf Keras losses, because we're dealing with binary classification. It's binary cross entropy. Little quiz. What would it be if we're dealing with multi-class classification? Optimizer, we're going to keep the same. We're going to use SGD, stochastic gradient descent, and the metrics we're going to set to be accuracy. Oh, this is going to be so much better. Fit the model. All right, model2.fit x, y. By the way, if you already guessed what we did wrong up here, we fit on the same data that we evaluated on. What should we ideally do? We should fit on training data and evaluate on testing data. But, well, because we're working with a toy problem, we're allowed to fudge what we're doing a little bit here. And now epochs. What should we do? Maybe 100. That should be enough. We've got 2 layers. I mean, this model should be great. Ready? Let's run. Now, number 4 can be evaluate the model. Because we set verbose equal to 0, we don't have very much output, but we should have a trained model 2. Evaluate, again, evaluating on the same data we trained on. Not ideal, but in our case, we're just trying to see if our model's learning anything. What? The loss is about the same, even with an extra layer, but the accuracy is still 50. So right now, our model is still not even as good as guessing. Like, it's getting 50% accuracy. Like, you could do that if you just, for every sample, if you had 1,000 samples, if you just guessed, let's see how many there are. Let's go here, code, and circles, label, which is y, value counts. So 500 and 500. If we just literally went and tried to guess red, blue, red, blue, red, blue, we'd be getting the same results as our current neural network with 2 layers. This is preposterous. What we should do in the next video then is that if our model's still only getting guessing results, we need to pull out a few more bags of tricks to improve our model. So, have a think about, refer to our architecture of a classification model and have a think about some of the things using my cursor in an area that might reveal something to you, by the way. Have a think about some of the things that we haven't yet included in our model and see if you can figure out why our model hasn't learned anything yet. But if not, I'll see you in the next video and we'll see how we can improve our classification model. All right, so we've built a few classification models so far, namely Model 2 and Model 1, which is a little bit further up. There we go. However, we've seen that despite adding an extra layer, Model 2 is still performing very poorly. I mean, it's getting 50% accuracy on our binary classification problem. And since we've got an even amount of samples for each class, so if we look here, we've got 500 samples of number 1 and 500 samples of 0. Now, or 500 samples of a blue circle and 500 samples of a red circle. Now, if you were to toss a coin 1,000 times, you kind of expect about 500 heads and 500 tails. Hence why our model is essentially guessing. So we have to look into our bag of tricks to see how else we can improve our model. So let's look into our bag of tricks to see how we can improve our model. Now, recall back from the previous section where we went through the steps in creating a model, or the steps in building a model, that is. But as you might remember, there are steps from within each of those steps that we can try to improve our model. So if we go create a model, that's number 1. 2 is compiling a model. And 3 is fitting a model. What can we try here? So when we create a model, we might want to add more layers or increase the number of hidden units within a layer. We've seen this. We actually tried this. We didn't increase the number of hidden units for model 2, but we did increase the number of layers. So we went from 1 layer to 2 layers, and that didn't really improve our model. What else could we do? Compiling a model. So here we might want to choose a different optimization function, such as Atom instead of SGD. Now, what optimization function did we use for model 2? We used SGD, so we might actually, Atom could be the next thing that we try there. And then fitting a model. So perhaps we might fit our model for more epochs. So leave it training for longer so that it might get a better understanding of what's going on or the patterns in our data. Now, these steps have just come from, if we refer back, this is what we've been through so far, steps in modeling with TensorFlow. Number 1, create a model. We've created a few models here. I want you to think about this one in particular, actually. There's a little part that we haven't quite covered yet, and it may or may not hold the keys to why our model isn't improving, but I'll let you have a think about that before we discuss it. Number 2 is compile the model. So we define the loss function, in other words, how wrong our model's predictions are. We define the optimizer, which is how our model should update its internal patterns to better its predictions. We define the metrics, which is a human interpretable values for how well our model is doing. We fit the model and we evaluate it. But now if we have a look at how we might improve our model from a model's perspective, we've got a few different ways. Adding layers, we've tried that. Increase the number of hidden units, we haven't tried that. Change the activation functions. We definitely haven't tried that, at least for the hidden layers. Change the optimization function. We could use SGD or Atom or one of the other optimizers in the optimizers package. Change the learning rate. We haven't tried that. Okay, so we've got a fair few things here that we could try. Let's start implementing some of these. And remember, because these are hyperparameters, or because these are changeable, they're called hyperparameters. So if we come back, instead of staring at our slide, let's write some code. How about we increase the number of hidden units? Yeah, and we'll add an extra layer. Let's do that. Set the random seed. So tf random.setSeed. I want to emphasize as well is that if you're thinking, well, Daniel, we don't really have a structure to what we're doing here. We're just trying things and seeing if they work. I mean, you're exactly right in thinking that. And that is a lot of what machine learning and deep learning is. Trying things and seeing if they work. Hence why our machine learning practitioner's motto is, I'm just creating a sequential model here, by the way, and I'm calling it Model 3. But our machine learning practitioner's motto is experiment, experiment, experiment. Now, we've created a first hidden layer here, and we're creating 100 hidden units in this one. So we're stepping it up from Model 2. If I create a new cell, I've turned that into Markdown. I don't want that. You can turn it from Markdown back into code, by the way, by going Command MY or Control MY if you're on Windows. Kara's layers dense. Wonderful. And we'll have the final layer there. So if we check Model 2, what we've done here with Model 3 is we've added 10 hidden units to the middle layer, and we've added an extra layer this time with 100 hidden units. So I'll put there, add 100 dense neurons, and this one is add another layer with 10 neurons. All right, This one should definitely work because we've stepped it up a notch here. I mean, if our model with 2 layers didn't work and only 1 hidden neuron, well, it definitely should work with it with 3 layers and over 100 hidden neurons now. Compile the model. So model 3, compile. What do we have to do for compile? We define the loss function, which is how wrong our model's predictions are. For a binary classification problem, we use binary cross entropy. And then the optimizer. Oh, this time I think we might also change atom or change to atom from SGD. Let's try that out. Why not? Metrics equals accuracy, which is a very standard baseline classification metric, but may not be the best one depending on your problem. We'll see other classification metrics in a future video. Oh, 2 equals there. We don't want that. And now we're going to fit the model. Oh, I can't wait to see the results of this one. 3 layers, over 100 hidden units equals, let's go for 100 epochs. What do we do model 2 for? I think we only did 5. Oh no, we did 100 as well. So we'll just do 100 this one. Verbose equals 0, so we're not outputting a lot of information. And shift and enter. Did we get any errors? No. Beautiful. All right. So let's see how number 4 is evaluate the model. So again, not necessarily a great idea to evaluate on the same data set that we've trained on, but for this toy example, we'll keep it like that. Shift and enter. What? Bow, bow, bow. What? We're still getting 50% accuracy. We've pulled out our few tricks. We've changed the optimizer to atom. We've added an extra layer, this time with 100 hidden units, and even another one with 10 hidden neurons. We're still getting about 50% accuracy, so just as good as guessing. You know what we're going to have to do? We're going to have to visualize. What do you think we should visualize in this case? If we want to see how our model's performing and the evaluation metrics are telling us it's not performing pretty well, what's another thing that we can visualize? How about we visualize the predictions? Yeah, I think that's a good idea. So in the next video, we'll make some predictions with our trained model and see, we'll plot them against, where's our graph? Here. Yeah, let's make some predictions on this graph and we'll plot what our model's predicting, how to separate these blue and red circles, and we'll see what they look like, just so we can understand what our model is trying to, or what the pattern our model is trying to figure out between these 2 circles. I don't think it's very good. So give that a play around. Maybe you want to try a few more things before we plot those, but otherwise, I'll see you in the next video. In the last few videos, we've been building models to try and classify our toy data set here of blue and red dots. However, they're all performing pretty poorly. Like, I mean, as good as guessing, even we've pulled out a few tricks to improve our models. So what we're going to do in this video is, if we come back to our Keynote, and we remember our Machine Learning Explorer's motto, visualize, visualize, visualize. It's a good idea to visualize these as often as possible. We visualized our data, we know what it looks like. We visualized our model, we know the layers and the different components of that. We've seen it train. We haven't plotted a loss curve just yet, but we don't need to because we know it's performing poorly. So let's test out, try visualize some of the predictions that our model is making. Now, how might we do that? We could do it like this. We could go model3.predict x and see what's happening. All right, we get some values there. They're all sitting around, that's a little inkling. They're all sitting around 0.5, but we want them to be closer to 0 and 1. All right, so that's a little inkling there, but I prefer to see things visually. So let's get rid of this. And to do so, what we might do is make a function, a plotting function called plot decision boundary, where what we want is, do you remember with our regression model, we had some data that was like a line, and then we plotted our model's prediction as a line compared to the actual data? Why don't we do the same thing, but with this circular data? Plot our model's predictions against the actual data. So to do so, let's create a function right here to visualize our model's predictions. Let's create a function. I'm going to call it plot decision boundary, because a decision boundary is just basically where's our model deciding where the bounds are between red and blue dots. And this function is going to, this function will, that's a better option. So we need to take in a trained model, features, X, and labels, Y. So those are the parameters. And then it'll create, might turn this into Markdown actually. Create a mesh grid. If you're not sure what a mesh grid is, it's a concept in NumPy. So NumPy mesh grid. That's what you can do for anything that you're not sure. Just search it up and have a little play around and figure out what it is. NumPy mesh grid. You could read the documentation there, or we could just practice coding it. Create a mesh grid of the different X values. And then we're going to make predictions across the mesh grid. And then finally, we're going to plot the predictions as well as a line between the different zones where each unique class falls. Now, right now, these steps are all just in English. They may not make sense. So let's start to write code for it. We'll go here, import NumPy as NP, and then we'll create our function, def plot decision boundary, model X and Y, and there we go. And then we're going to put in a little doc string here, so we're being nice and Pythonic. So plots decision boundary created by a model predicting on X. Beautiful. So the first thing we have to do is we've taken in a trained model. So there's our model parameter, there's our features, and there's our labels. Now, let's define the axis boundaries of the plot and create a mesh grid. So we want the X minimum and the X maximum is going to be, we can index on X to get both of these values. So we just want the 0th axis, the minimum, and we're going to minus 0.1 to give ourselves a little bit of a margin. And the same thing with the maximum. So we just want the 0th axis, and then we take the max, and then we're going to plus 0.1 to give ourselves a little bit of a margin there. And then we can do the same thing for the Y min and the Y max, except we're going to index on X and get the first axis. Dot min, the minimum, and the same thing here. Semicolon, 1 dot max, plus 1 for a little bit of a margin. Now, if you're not sure what these values are, what can you do for any type of function? You can just take the code, copy and paste it, or probably better to write it yourself, and then xmin to visualize them. This is what we want to look at all the time. Line by line. I'm not going to deconstruct this function line by line, but if you wanted to understand any function, this is what I do. I take the line by line, and then I visualize it in a single cell. So here's the values. These are our boundaries, and now we can create the mesh grid. YY equals, now again, this is coming straight from the documentation here for mesh grid, is np.meshgrid, and then in here it takes linspace. Now how do we figure out what something does? We can do command shift space. Oh, we haven't imported NumPy yet. That's why we can't run this function or can't get the doc string. We'll import NumPy up there and see what linspace does. Here we go. Return evenly spaced numbers over a specified interval. Okay. So if we did 0 to 10, it might return evenly spaced numbers between 0 and 10. Beautiful. But we want evenly spaced numbers between our x min and x max, because this is going to be the first parameter of our mesh grid. And then we want the same thing for y min, y max. And then we're going to go 100. So here's the minimum, here's the maximum. Return 100 values evenly spaced between x min and x max, and create a mesh grid out of this one and this one. If you want to see what that looks like, again, you can copy this and probably put it in a code cell below. Otherwise, let's push forward with the function. There we've created our mesh grid of the different x values. Now it's time to create x values. We're going to make predictions on these. So x in equals npc. Now we want to unravel xx by passing it to ravel, yy, ravel. And if you're not sure what c does, you can go, what can we do? numpy.c. User manual. Translates slice objects to concatenation along the second axis. So if we pass it in two arrays like this, what does it do? They were stacked and now horizontal. So that's what's happening here. So stack 2D arrays together. Now we're going to make predictions using our trained model. We've passed it in with the model parameter here. So we go ypred, which is our usual variable name for any type of predictions. Model.predict x in. Alrighty. And now we're going to add a little bit of functionality here that we can check for multi-class. We're working with binary classification, but let's check for whether we're working on a multi-class classification problem. This will help make our function usable if we did want to, if we had red, green, and blue circles instead of just red and blue. So we can check the length of ypred for the first sample. If that's greater than 1, print doing multi-class classification. And then if so, we have to reshape our predictions to get them ready. Now here we got to go ypred equals np argmax. We haven't seen this before. We could use tf argmax as well. Ypred axis equals 1. Reshape xx.shape. So we're reshaping it just to the shape of xx up here. Now let's make else. If they're binary, we'll print doing binary classification. So this is just the else statement for this little if condition here. And then ypred equals np round. So we're just rounding our prediction. Ypred reshape to xx.shape. Now we're finally up to plot the decision boundary. Again, this function has a fair few steps, but again, if you want to understand it, take them out, deconstruct it, and look at what's happening line by line. That could be some homework for you after this video. YY. I want to contour plot. So what is this? Plot contours. Nice and succinct definition from that documentation there. Thank you very much. But again, we're going to see what this looks like rather than just reading docs. We're going to write as much code as we can. Alpha. Wonderful. And we're going to plot a scatter. We need to plot the 0th axis of x and x's first axis. And color this in y. S equals 40. Now what does the S parameter do? Where is S? There, scalar. So the marker size in points. So this will define how big the size of the scatter plot points come out. And then we're going to plot CM, RD, yellow, blue. This is our color. And plot xlim. We want to set the limitations. So this is where XX minimum comes in and the XX max comes in, as well as the Y limitation. We can do the same thing for YY, min, and YY dot max. Whew. Okay, that's probably the biggest function we've written so far. I mean, it almost doesn't fit on the screen. A lot going on here, but now that we've got a function to plot our model's decision boundary, I mean the cutoff point between the decisions it's making between red and blue dots, let's try it out. So we go here, we'll run that. Hopefully there's no errors. Check out the predictions our model is making. So if we want to plot decision boundary, we pass it in our trained model, which is, we'll set model 3 because that's our most recent model. X is just X and Y is equal to Y. Remember, X and Y are just our features and labels. So again, 1 point here, leads to a 1 or a 0. We'll get rid of that. You ready? 3, 2, 1. Oh, would you look at that? So, this is why our model is performing so poorly. It looks like it's trying to draw a straight line through the data. Now, what's wrong with this? Well, we've got circular data. So the main issue here is that our data isn't separable by a straight line. But if we were working on a regression problem, what is a regression problem? Now, in a regression problem, our model might actually work because it's drawing a straight line. So how about we test that? We might do that in the next video. And as for this function, if you're wondering, Daniel, how did you learn how to create all of this? Well, the truth is, I've borrowed this and I've adapted it for our use case. So if we come here, one of the resources I used was CS231N, Neural Networks Case Study. Now, this is a phenomenal course, Convolutional Neural Networks for Visual Recognition. We haven't actually worked with convolutional neural networks yet. So if you go through this, it might be a bit full on, but I'd highly recommend this, as this is going to be a part of the extra curriculum for this section and the convolutional neural network section. So if we come down here, I dug into the code behind this material here, and I found this. So they've got some spiral data here, and I've just changed it for our circular data. And I'm going to put this link in here. This function was inspired by 2 resources. Number 1 is this one. And then number 2 was another phenomenal resource, Made with ML. So if we go to Made with ML GitHub, and then into the basics. So this is a phenomenal repo. I highly suggest you star this one. I definitely have. If you want to learn more about machine learning and deep learning and how to code them, there are some amazing notebooks here. So I got it from this one here, the multi-layer perceptrons. We come in this one. Oh no, that's for PyTorch. We come into TensorFlow. Now there's a function in here somewhere, very similar to the one we have. Boom, plot multi-class decision boundary. So there we go. So I'm going to copy this resource here. Number 2 is there. So I'll make sure to link those in the extra curriculum. But in the meantime, let's try and adapt our neural network to see if it works, even though we're working on classification right now. Because our neural network is plotting a straight line here, or predicting a straight line, I wonder if we can adapt it to a regression problem. Let's check that in the next video. In the last video, we created a function, plot decision boundary, to visually inspect our model's predictions, and we found that it's performing so poorly because it's predicting that the decision boundary is a straight line, whereas our data is circular. So we have a linear decision boundary, which linear is a fancy word for straight line, and we have non-linear data, which is another fancy way of saying non-straight data. Now, if we come back up here, I've just added a little tidbit in here in retrospect, but we've already discussed this. It's that, remember, wherever you see the key, it's an important point to note. Whenever your model is performing strangely, or there's something going on with your data you're not quite sure of, remember these 3 words: visualize, visualize, visualize. Inspect your data, inspect your model, inspect your model's predictions. And that's what we've done here. And we also discussed that since our model is predicting a straight line, might we be able to use it for a regression problem? Let's have a look. We'll write some code. Let's see if our model can be used for a regression problem. Now, we'll need some regression data. Now, I'm going to set the random seed here because we're going to create some regression data. And we'll make x regression so we don't override our already existing x variable. And I'm going to do tf range 0 to 1,000, and the step can be 5. And then y regression can be TF range 0 to, oh, actually, let's start from 100. So the function here we're trying to predict is just y equals x plus 10. That's the relationship between x and y here. Oh, sorry, plus 100, because y starts from 100, finishes at 1,100. X starts from 0 and finishes at 1,000. They both have the same step. So let's check this out. Remember, visualize, visualize, visualize. Inspect your data. Become one with the data. So there we go. Starting from 0, stepping up by 5, all the way up to 995. Starting from 100, stepping by 5, all the way up to 1,095. So we can remove those. Let's split our regression data into training and test sets. XReg train for X regression can be, let's just make it, how many values? We've got 1,000, so there's 200 total. And let's do the first 150, can be for the training data set. And the last 50 can be for the test data set. So XReg test equals X regression. We want just the last 150, so 150 onwards. That's how we can index that. Then we'll do the same thing for the Y data. We could have actually done this for our circles data, but we'll move on from that one. We'll do that later on, I think. And then we go there. And now let's see. So we've got training and test data. Let's see if we can fit our model. Fit our model to the regression data. Wonderful. Model3.fit. Now before we do this, I want you to have a think. Will this work? Go back up, scroll back up in the notebook. I'm not going to give you any hints, but just step through each of the steps that we use to create Model 3. Build a model, compile a model, fit a model. We're doing step 3 right now, fit a model. Will this work or will it error? Inspect how we created it, inspect how we compiled it, think about the problem we're working on, regression, and have a think, will this work? I'll give you about 3 seconds or so to try that out. Well, I mean, you can pause the video, but 3 seconds for me. 3, 2, 1. All right, did you figure out why it will or won't work? You know what I hope you did? I hope you ran the code instead of scrolling back up. I hope you just tried it, because that's what I'm going to do. Oh no! What's happened here? Input 0 of layer sequential 2 is incompatible with the layer. Expected axis of -1 of input shape to have 2, but received input with shape none 1. So what's happened? We've got a shape issue, one of the most common issues in deep learning. So what's going on? We got train. Yeah, we've created our data sets correctly. Why hasn't our model worked? I wonder. So we've compiled our model for a binary classification problem. So we come back up here. Where's Model 3? Compile the model. We've set the loss function to be binary cross entropy. But what should it be if we're working on a regression problem? It should be something like MAE or MSE, mean squared error or mean absolute error. So let's go back. How about we write here, oh wait, we compiled our model for a binary classification problem, but we're now working on a regression problem. Let's change the model to suit our data. All right, so the only thing we're going to change in Model 3 is the loss function. What I might do is get rid of this code so it doesn't interfere with what we're going to write. So if you want to try yourself, all we're going to do is just recreate Model 3 exactly how it is. We're going to change the loss function. Instead of being binary cross entropy, we're going to change it to mean absolute error, so that the loss function is regression specific. So give that a try, and otherwise I'm going to start writing it now. So we've got to set up the random seed so we get reproducible results. Set seed 42. Now step 1, we're going to create the model. We'll just recreate model 3. It's all right, we can override it. TF Keras, and plus, what's the harm in having some more practice writing model code? TF Keras. By the end of this course, I want you to have created over 100 models. Maybe even more, who knows? I'm not actually sure, I haven't counted. Maybe someone out there could count how many models we actually build together and then let me know, because that'd be pretty cool. You know what I should have done? I should have increased this number so we just knew the whole time what number model we were up to. Too late now. And so compile the model. Now this time with a regression specific loss function. Beautiful, model 3 dot compile. Loss equals TF Keras, losses, MAE, beautiful. And then the optimizer can be TF Keras. We're going to keep the optimizer the same. We'll keep it as Atom, optimizers.atom. Remember, Atom is safe. Metrics equals, we need to adjust the metrics as well because it's a regression problem. We'll keep MAE there. And finally, 3 is fit the model. So we have model 3, we've recreated it, dot fit on X reg train and Y reg train, which is our regression data set. And we'll set it up for 100 epochs. Now you ready to run? 3, 2, 1. Ho-ho, there we go. Now what did it start with? Did we have, so the MAE is close to 250. And by the end, we go right down to 37. That's beautiful. So we see a reduction in loss and a reduction in MAE. But to make sure, seems like our model's learning something from these training metrics. Let's plot them. So just like we've plotted our circular data, we'll plot our regression data. So make predictions with our trained model. Y reg preds equals model3.predict X. Make it on the test data set. Oh, sorry, it's going to be, predict X reg test. Yeah, that's what we want. And now let's plot the model's predictions against our regression data. So we can create a plot here. We're not going to write as big and intricate a function as we did for our classification data, because this is regression data is just a straight line. And we're going to do a scatter plot. And on this scatter plot is going to be the training data. So X reg train, Y reg train, and the color of the training can be blue. We'll label it training data so we know that it is the training data. Create another scatter plot, this time for the test data set. So test features and test labels. And we will color this with green and give it the label equals test data. And plot scatter X reg test. And now let's plot our reg predictions. And we're going to have to, no, I think that should be okay. We might have to, I wonder what dimension they are. Well, we'll check. If in doubt, run the code, wait for the error to pop up for us, and then we can see. And then plot legend. So that's what we've done. We've trained a regression model. We adapted model 3 to be suited for our regression data. We've made some predictions on the test data set. And now we're just plotting it, just like we did in the regression section. Training data, test data, predictions. Let's go. Figure. Oh, we want this to be fig size. Oh, would you look at that? Okay, so the predictions aren't perfect. I mean, if they were, the red line would line up perfectly with the green line, but they definitely look better than complete guessing. I mean, imagine if the predictions were all over the shop, like red dots everywhere. That would be basically guessing for this regression problem. Now, this means that our model must be learning something. However, it's still missing something for our classification problem. What's the difference here? What is the main difference between our data sets? I'll give you a hint. This regression problem is a straight line. Whereas if we come back, we discussed this before, our classification data is not a straight line. It's non-linear, but the decision boundary our model's trying to plot is linear, straight line. So, That might be the missing piece, the thing that we haven't introduced to our models yet. We haven't introduced nonlinearity. And if you haven't heard of that before, that's okay, because we're going to discuss it in the next video, and probably maybe a couple of videos after that. So let's write that down. The missing piece. It's like we're on a treasure hunt here. Non-linearity. Alrighty, get excited, because we're going to learn one of the most important concepts in neural networks. Woohoo! I'll see you in the next video.